Good morning and welcome everybody to Engineering Tomorrow's Renewable Energy event. We are so excited to have so many groups from across America here live for our event today. We have the amazing Carla McQuarrie who's going to be leading you all today. She is the star of the show for now, but just so you know, you guys are going to be the star in the wrap up. So I hope you guys are getting ready. Pay attention during the introduction, get building, and then we want to hear from you all. We love chat, so please get your teachers in the chat. Let us know if you have any questions, but I'm going to stop speaking and let Carla take it away.
Excellent. I'm so excited to be here with you all. And just like Monica said, you guys are really going to be the stars of the show. You are the main event because we are so excited to dive into this lab with you. And I just want to, before we start, give a real shout out to the team that helped develop this lab. What I love about these labs is that we treat them just like an engineering project, right? We listen to figure out what we want to communicate, and these teams get together and they put together really incredible content. But we get to also work with student mentors that are in college so that we try to keep it really relevant. And for us dinosaurs, that might be a little bit further away from high school than others, right? So huge shout out to Eric Einset, who was the engineer staff that worked on the development of this lab, and our college mentors that also helped with the most recent reboot of it. So Anna and Jackie. So my name is Carla McQuarrie, and I'm coming to you from Nova Scotia, Canada. So way up north. It's actually not too cold here today. So I'd love to put in the chat what your temperature is looking like there today. So what you see up here on the screen is a contaminated site. So I am an environmental engineer. I've been practicing for 25 years. I have a Bachelor of Engineering. And so that's a 5-year program where I'm from. And then I also, after working for a couple of years, decided to go back and get my Master's of Applied Science. And that was specifically in the area of water quality. And so what I love is I love to share just to kind of give people a picture of what an environmental engineer might do. So what you see up on the screen here is a contaminated site, and it's way up north in Canada, very, very remote. And actually, I'd love for you to put in the chat if you can think about why we might be interested in renewable energy at a site like this, okay? And so I love to share this because it's probably pretty clear for you to see why an environmental engineer might work on a contaminated site like this. But I get to work with all different types of engineers. I work with structural engineers when we're constructing buildings. I work with mechanical engineers when we're sizing our pumps. I work with conveyance and civil engineers when we're designing how the water will move around the site. Computer and robotics engineers when we're setting up all the different controls for our water treatment plants. And so this is just to say that there is so many different types of disciplines in engineering that end up being involved in lots of types of projects and different kind of problems that exist in the world. So this is my passion. I love the environment. I love working in water quality. And so I was able to find something that I was really passionate about very early on. And I hope that while you're going through these different labs with Engineering Tomorrow, and particularly this one, you're thinking about what kind of things interest you and how can you maybe apply them, or what kind of engineering areas might be appropriate or relevant to the things you're really passionate about. I'm really excited to introduce you later to Alex. So we're going to be hearing from Alex Coleman, who is actually on the board at Engineering Tomorrow. She is the head of Centuric Business Solutions North America, and she has lots of experience, technical, financial, and she has a lot of experience, particularly in renewable energy. So that's going to be really exciting. Okay, we are going to just have a little bit of interaction first. So we're going to be hopping onto a Slido. So if you guys have access to phones or computers, you can hop onto slido.com, or if you have your phone, you can even use that QR code that is up here right now. Okay, so hop onto your Slido. I know there's lots of us here, so I'm going to move right ahead. And our first question, okay, and I want to make sure, let's keep it really clean here and appropriate. What word comes to mind when you think of an engineer? Okay, I got lots of people typing. I cannot wait for these words to come in. Okay, power, building, creator, efficient, inventor, science, creative, construction, smart, smarty pants. Okay, I'll take that as a compliment. Creation, solver, being licensed, that's a good one. Engineers are a lot of times licensed. Problem solver. Oh my gosh, these are such great words. I love all of this. I love all of this input that's coming in. Power, science, manufacturing. Okay, so as you guys are thinking about all that, I really want to just break it down and say one of the simplest ways for you to think about engineering is just simply problem solving. That's what is so cool, is that problems exist in all different areas, right? Whether you're talking about sports and you're talking about medicine, whatever area exists, whatever areas you're interested in, there are problems that exist in the world. And that's all that engineers do. Engineers take a problem and they apply what they've learned in math and science and all the different areas, all the different things that we learn in the textbooks and all the theory, and we apply it to real life problems, right? So even what we're doing here right now and getting to have all of these classrooms here virtually together, all across the United States, we're all interacting, sharing information. We are doing that because it's a virtual technology that has been developed to meet a need, right? We had this need to be able to communicate virtually, and so people come up with solutions. So if you think about engineering in the most simplest term of problem solving, of looking at what problems exist in the world and how to solve them, then that is what engineering is about. Lots of times we think, we see a lot of things where people think construction or bridges and building and really, really hardcore. And yes, that is an important part of engineering. But at the very bottom, at the very end of the day, the most foundational piece is solving problems. So now that we're thinking about that, let's jump into our actual lab. And because all of you are going to be engineers today, you all get to be engineers, and because you're going to be solving some problems. Okay, so next question on the Slido. Let's think today. If you could, what would you use solar power energy to power? If you could just instantly have one thing that we could easily power with solar energy, I bet you there's something here that you guys often have to plug in, right? What's something that you have to plug in a lot? That if you could have an easy access to solar energy would be great. Your phone, right? That one, that I'm expecting would come up. But of course, houses, there's so many different things that would be amazing if we could actually be having solar energy. And I'm just having a little trouble finding my chat here, because I want to make sure I'm not missing anything in the
The Zoom chat is clear, Carla, so you can keep going.
Okay, perfect. You let me know, Monica, if there's anything that comes up.
Will do.
Perfect, thank you. So that's a really cool thing, and that's what we're going to get into today, is thinking about how can we start to harness some of the different types of energy that exist and actually be able to power different pieces of our life, right? Tell me this, what are some of the alternative sources of energy that you know about? Right, so outside of fossil fuels, like outside of going and just getting a regular kind of coal and oil and petroleum, nuclear, wind turbines, solar, hydro. Hydro is really cool. There's one it's kind of related to hydro that I'm not seeing up there yet, tidal, right? So yes, it's related to the ocean, but it's actually related to the tides and controlling tides. We have wave energy, solar energy, wind turbines. You guys are amazing. So you should come in. I'm expecting to see some really cool labs today, because you're already have a really great starting point for what types of and why it's so important to have renewable energy. So like I mentioned on the project that I was working on, there's also lots of types of engineers that work in renewable energy. We have materials, right? Really having ability to store energy and new battery technology, that is so important. That's all related to materials. We have electrical engineers, control engineers, mechanical, civil, aerodynamic, materials, environmental engineers. So if you're interested in the field of renewable energy, there are lots of different pathways that you could actually take through engineering to be working in this field. Okay, so let's talk about what we're going to be doing in this lab. We're going to be looking specifically at how we can trap and harness power from the sun, and how we're going to trap and harness power from wind. And you are actually going to be designing and building a hybrid wind and solar structure to light up some LEDs. And let's get right into it. So before we get started, you do have to understand some of the fundamentals about power and energy and how they work, right? So if you've done your physics before, then you will remember that energy comes in a couple of different forms, right? We have kinetic energy, potential energy, and energy is really the capacity to do work, right? So maybe lifting something, we're going to heat something, we're going to spin a turbine. That's the actual work that we're doing. And power relates to how fast we can do that work. So I love this analogy that Eric has shared. If you're running a race and you were running a really short sprint, then you need a lot of power. You want to be really fast, right? It's all about the immediate power. Whereas if you're a marathon runner, you need a lot of energy. So throughout the lab, what you're going to be looking at, you're going to see different units. I know you're all familiar with how important units are. We're going to be talking about energy in terms of watts, watt hours, and yes, there are different forms of different units for energy. We have joules, calories, BTUs, but when we're talking about electricity, we're going to be talking about watts. And you can see here a couple of examples, right? We've got the regular incandescent light bulb, that's around 60 watts. And then we start to move into different technologies where we can be emitting the same amount of light, but with using less energy, right? So when we go to an LED bulb, we've got 7 watts. And then just to kind of give you some perspective, like a refrigerator is obviously a much bigger energy demand than a regular light bulb. But I always like to use that as a reference point when I think about and I look at maybe the Energy Star rating on a particular appliance. I think about it and go, okay, how many light bulbs would that be? Right? And how many of you have had somebody in your life say, turn the lights out, right? You leave a room and you forget to leave the lights on. Well, this is why, is because we're consuming energy by those light bulbs. And so you want to always be thinking about how many light bulbs would this be? Okay. And then we're going to be talking about some really large numbers because energy is often expressed in, we're talking thousands, the kilowatts, the gigawatts, the megawatts. It is a lot of energy. So just imagine like if we were having how much energy we would need to power an entire city or an entire country. So we're talking about really big numbers here. And so then when we think about that, let's just look at like a little bit about solar and wind. You start to see much bigger numbers in terms of how much energy we could be harnessing. So regular sunlight, the heat of the sun, that is being converted at 1,000 watts per square meter or a kilowatt per square meter. The same thing with wind, right? So if we have a really, around 20 miles per hour brisk wind, that would be 1750 watts or 1.75 kilowatts per meter square. And so how do we capture that? Right? So that's part of the challenge is how do we get an area big enough to really capture that energy? So, if you have a kite, if you're flying a kite, the bigger the kite, the bigger that the more energy, the more power that you're going to have in that kite when you're flying it. Same with if we had a sail, the bigger the area, the more capacity that you're going to have to capture that energy. Okay, so let's get into the wind power fundamentals. So wind turbines, this is what allow us to harness the power of the wind and turn it into energy. And so what you're seeing here is like a really mammoth size wind turbine, right? So if you can compare, see that little circle down there at the bottom, that's a person. So if you can see relevance perspective wise, how small that person is compared to these big, big wind turbines. So these towers, they're made of steel, concrete, they're huge, and they're going to be sturdy enough to support the structure of the actual turbine. And we know that wind, of course, the higher we are, we need to have really tall towers to get these turbines in a position to capture more energy and be able to create more electricity. Then we have the nacelle that's sitting up on the top of the tower, and it contains the gearbox, the low and high speed shafts, the generator, the controller, the brake, and some of these are large enough that we could actually land a helicopter on them. And then we have the blades, and the blades are what are lifting and rotating when the wind is blown, causing them to cause the rotor to spin, which is all part of the whole process. So we have, when we look at how it's working, we have the kinetic energy of the wind, which turns those rotor blades, making the mechanical energy. So we convert the linear flow into rotational energy in the rotor. And this rotation is connected to a gearbox within the nacelle, which then changes the speed of rotation of the subsequent rotating components. And the gearbox output rotation is connected to a generator, which then converts that rotational energy to electricity. And then we go through the whole process. It travels down the transformer, and then it gets put to a different voltage level to adjust it so that it can be in the form that we can consume it, right? Because we can't take it. And that's why we always see the different, when you're looking at different power grids, those are stepping down the power to make it usable to us in the form that we need it. Okay, so we're going to be going through and actually looking at how to convert the power of the wind from a wind turbine. So this will be part of your student workbook, and we have a lot to cover here. So we can answer any questions when we're actually getting into the lab itself. So let's think about some of the limitations if we were building a wind farm where we're putting, and a wind farm talks about where we're going to put multiple of these turbines together. What kind of factors do you think that we would be looking at? Right, so we know from that equation, we have to think about the most important factor is the wind speed, right? So that's why a lot of times we're going to see these wind turbines on areas like, this ridge, this mountain ridge, or in the middle of the ocean, or a really flat plain. So, but can anybody put in the chat what some of the other limitations might be with some of these really great locations in terms of optimizing how much wind we can harness? What are some of the challenges with this? Right? Location. Yeah, it's amazing if we can put these wind turbines in the middle of the ocean, but then how do we get that electricity converted back to where we actually need to consume it? Same with up on these mountain ridges. And there's also a lot of times very big environmental issues that we have to be aware of where we're going to be placing these wind turbines to make sure that we're not disturbing or causing any harm to the local environment. And so this is where it becomes really complicated, and we have to really think about a lot of different factors when we're looking at where we may want to put these wind turbines. So this is actually a really cool video we're going to look at that is for assembling a wind turbine. Okay. Oh, I should be able to play it right in here.
Say farewell to video imperfections with
We
Iris,
don't
the
have the video
groundbreaking face
there
enhancement
it is.
AI designed exclusively for video.
I think
See
your
the
Wi-Fi is a
difference
little
as Iris
slow,
works
Carla.
its
It's not
magic on interlaced,
showing
noisy,
the
or
video.
compressed footage with degraded
No?
faces.
No.
Forget unnatural
Okay, let's
enhancements.
skip over that
Iris
then.
uses advanced information from multiple
hear the
frames
audio,
to
but we
achieve
don't see the
stunning
video.
and
I know what we're
natural
doing.
and
Yeah, we're
detailed face
speaking the audio
enhancement.
here.
Iris eliminates
I'll
flickering
just
and
close that one, and we'll put it on. So let's see if we can get it to play from here. Oh, it keeps taking me over to the YouTube version. Okay, usually I get a little play button here. Okay, so let's keep moving on. So there is going to be in your student workbook some great videos that you can watch when it comes to actually how they go about assembling these wind turbines and understanding the magnitude, because these are really, really huge. So we've got some great images here too of installing a wind turbine offshore. So you can see, can you imagine the complexity that goes into some of these projects, right? Of getting these, the structure and the tower constructed in these really, really difficult environments. Okay, so now we're going to move on to solar power, because that's going to be the second part of our lab, is looking at some of the basics of solar power. And so this slide really illustrates the potential solar power. We have energy from the sun being the largest energy source available on our planet. The entire world's energy uses 16 terawatts a year, and it's only a tiny fraction of the sun's 23,000 terawatts, right? So 16 compared to 23,000. So traditionally, we looked at some of those sources of energy, like we have coal, oil, natural gas, uranium. These are finite resources that eventually we are going to run out of. And so renewable energy sources like wind or solar, they are continued to be available year round. And for these sources, the amount of energy shown, so you can see comparatively how much energy we can actually harness from these different resources. So solar energy share of the total energy market is currently well below 1% of the total energy consumption, compared with roughly 85% coming from oil, natural gas, and coal. But the problem is these fossil fuels are limited in supply, but they contribute a lot of issues to our air and our water pollution problems. So including the buildup of carbon dioxide in the environment. And so figuring out how to leverage and really tap into the solar energy is very critical to meeting our current and our future world's energy demands. So we have two different types of solar energy plant designs. We have the PV, the photovoltaic plants, and we have the thermal solar plants. And so you may have seen solar panels on the rooftop of people's buildings or of their homes. And there's also solar energy plants that capture energy and convert it to electricity. So this is a type of a photovoltaic cell that is used to directly produce an electrical current from the captured sunlight. And that's what you're going to be working on with your labs today. And the other kind, the solar thermal plant, uses mirrors to concentrate the sun's rays to heat fluids that then create steam, which also drive a turbine and produce electrical power. But we're going to be working with the photovoltaic cells with our lab. And let's see if this will play from here. I'm missing my little play button. I'm not sure what happened to it. I usually can see it. But again, we want to make sure we get through all the material. So let's just keep going. So let's think about how a photovoltaic cell works. The photovoltaic cell, which as the name implies, it's talking about light, and then voltaic meaning energy, they are going to convert the sunlight directly into electricity. A solar cell is a really great example of an engineered material, and research is continuing to make these more efficient. And we know it. I don't know if you've even looked at the size and the construction of them from even 20 years ago compared to what you see now. They're just changing exponentially. And why is that? Right? We talked about, what do engineers do? Engineers solve problems, right? So we constantly want to make these products better and better. So that's where the research is going into. So these PV cells, they're made of special materials called semiconductors, such as silicone. And when light strikes the cell, a certain portion of it's going to get absorbed within the semiconductor material. And that means that the energy of the absorbed light is transferred to the semiconductor. And then the energy knocks the electrons loose, allowing them to flow freely. So PV cells also have an electrical field that force the electrons freed by the light absorption to flow in a certain direction. And this flow of electrons is a current. And by placing these metal contacts on the top and bottom of the PV cell, we can draw that current off for external use, right? So for example, you may have a calculator that has a little photovoltaic cell on it. So we can draw from that current to actually power things that have a smaller energy demand. So this current, which is the result of the built-in electric fields, defines the power or the wattage that solar cell can produce. So we've been given, I'm going to skip this one because I want to make sure we finish up here. So 0.5 volts is not a lot, right? So this is one of the challenges, is how do we convert the solar energy to grid energy, right? So if 0.5 volts is not a lot, so to take advantage of the sun, we often have to connect a lot of these different cells together in series to create a module. And the way to get more voltage is to connect these series, plus to negative to positive, positive to negative, and then your total voltage will be the sum of all those individual voltages. So for example, in a typical panel or a module, you could have 72 cells in series that could give you approximately 36 volts. And if you have two panels connected in series, you'll get 72 volts. Of course, one of the challenges is that we aren't always able to consume the energy exactly at that moment when the energy is being produced by the solar panels. And then another challenge, of course, if you can imagine with solar energy, is what? What's one of the limitations of solar energy? The fact that the sun goes down, right? So we don't always have the availability of solar energy to be able to power things. So that's when we start getting into battery storage. So when you're thinking about where you're going to put your solar plant or your solar panels, we have to look at placement in terms of, because the sun doesn't strike all points on the earth at the same with equal energy, right? We know we've got different areas of the world that receive different amounts of sunlight. And the amount of energy received at any location on the globe is a direct effect of the sun's angle of incidence. And that means the angle that the sun hits the earth, and that's going to vary by location and time and season, and the daily rotation of the tilted axis and around the sun. So when sun shines on the earth at a lower angle, which means that the sun is closer to the horizon, the energy of the sun is spread over a larger area, and therefore it's weaker than if the sun was directly overhead. And so you can see this color-coded map here. It's showing the areas that have a higher potential for solar energy. And just as a little fun fact, the site that I showed you where I work up in the north of Canada, at this time of the year, they only have about 3 to 4 hours of sunlight every single day, right? So in the day, then coming in the summer, they only have 2 to 3 hours of nighttime where the sun isn't shining. So you can imagine how, if you were looking at solar energy in an area, in a project like that, you have to be really aware of how are you going to be able to do that through the whole year when you only have a few hours of sunlight and a very, very low angle in those hours. Okay, so let's get into what you are going to be doing with your labs. So these are going to be the components that would have been included in your lab kits. So you're going to have your generator and the bracket. You're going to have some different LED bulbs. You will have your propeller, your 5-volt solar cell, and 3 different your jumper wires. So the LED, so this is our light emitting diode, and your solar PV cell. So these are the different components that you're going to be working with. And don't forget, the solar cell is your source of power. So when the sun is shining on it, that's where we're going to be generating that electricity. And when you're making these connections, you're going to want to look. It's a very, very, very small difference, but one of the leads on your LED will be longer than the other. And that long that long leg of the LED has to be connected to the positive wire from the solar cell. So you're going to have your generator, your jumper wires, all these different pieces. And what your goal is because the way that the electrical circuit works is like this. The generator has a positive and a negative side. And the positive side is the red wire, and the negative side is going to be your black. So the electrical current will flow from the positive to the negative when the generator is spinning in the design direction, but only if the circuit is closed, right? So we need to have a full closed circuit. And so just as a little heads up, if you have something not working, you want to check all your connections. So the circuit also needs a load. It needs something to power to slow down the current. And the load is what is going to be our LED, or a light emitting diode. The LED, like I mentioned, will also have a positive and a negative. And it doesn't typically provide a lot of resistance to be a real load. So another load like a resistor could be placed in your circuit. But for this case, our generator will not produce a very large voltage for a long period. So you should see your LED light up when you get your generator spinning fast enough, okay? And the LED will light when it gets enough voltage, which is usually around 1.3 volts. Your wind turbine will have to spin pretty fast to create that much voltage. And even testing it myself, like you blowing it, and you might think that you've got it spinning fast enough, but you're going to want to use some other options, some other sources of wind energy to really test that out and make sure you can get your LED shining brightly. So you're going to be testing different things. You want to, once you've reached that threshold of your generator and you're actually producing that, the light is going to be stronger the greater the power your turbine is generating. So you're going to want to test things like how bright and how bright can you get that to shine. You want to try it with the different LEDs, because you're going to see that the different LEDs have a different load based on their color. So meaning that one LED will require more than the other. And you're going to want to try it out with using some kind of a source of wind, right? So a hairdryer or a fan to help spin that if you're not able to get it blowing enough outside. Okay, so you can test it by getting those spinning. And it's also really fun to test out different things to see, you know, we have things that are called startup, right? So sometimes getting it started up is going to be a little bit more difficult versus once you get going. So I'd love to see you test, if you have a hairdryer or a fan, what happens when you start it up. How close do you have to be to get it to start? And then slowly start walking away or increasing the distance from your source, and then reversing that to see when you come back in, how much closer, how far, once you get it stopped, when does it start again? Okay, so you might see that there's going to be a little bit of a difference between as you're moving away versus going towards. It's not going to be immediately the same spot. So just a couple of hints when you're getting ready to go into your lab. Remember, the plus and minus sides of the generator will depend on which way that it is spinning. So if your circuit's not working, you can try switching up your leads. And the LED does need to be hooked up in a specific way because the current has to flow in a specific direction or they will not work. So make sure that your live metal parts are not touching other parts of the circuit so you can actually tape them down to keep them from flopping around. So you're going to have a couple of components here, right? You're going to actually have your electrical circuit that you need to get going, but then there's also going to be the design. This is where you get to have a little bit more fun of determining what pieces, how do you want to build your design? And here's a couple of different examples of things that have been constructed. And you're going to want to be thinking about what are the different requirements as you go through this and testing out your design. So you're going to want to see, can you actually get your LEDs to light up? So really important, when you go into this, we're going to go through the engineering design process. You're going to be thinking about, before you start just constructing and trying to build things, you want to think about what are the goals of this? What are some of the constraints? We need to make sure that our fan is able to move freely and that we can control how we get the fan to turn. And you want to have maybe some architectural elements. What do you want it to look like? But you don't want to spend too much time in design. You got to move into actual execution. So our design process, we go through, we design things, we test it. So that then you're in testing mode. Then you're going to figure out what's working, what's not working. So that's your check mode. And then you're going to go back through and make some changes. And so you want to be documenting this process as you go. What does your design look like? Then you start constructing and testing it, make those changes. And what's really cool about engineering is that we don't look at failures as failures when we're in this phase, because we want to fail fast. We want to figure out what doesn't work so we can make those adjustments, make some changes, and move forward and keep going. Okay, so you have your student workbooks. You're going to be trying to all these questions. Can you get your wind design to work? Does the LED light up when you spin the turbine fast? What does your house look like? What do you want to achieve with your house? What point does the LED stop lighting? Does the solar panel light when it's facing the sun? So these are some of the questions you're going to be asking yourself. Okay, so let's get through. I think are good to go. Monica, is there any last minute instructions we want to have for them before we actually break in?
Yeah, so the breakout rooms, first of all, big round of applause to Carla for our phenomenal introduction today for renewable energy. I hope you guys are excited to get building and designing. She gave us some great tips. I hope you guys are all ready to use them right now.